Hello all, welcome to my course on methods of adhesion measurement theory and practice. We are today at lecture 29 and we are discussing about rolling contact mechanics, estimation of hysteresis. These are the list of references, and what we discussed today and we discussed in the last two lectures are taken from the last reference here, that is estimation of adhesion hysteresis using rolling contact mechanics. And here we derived this expression for the pressure at the contact area for this asymmetric contact. The asymmetry occurs because of the hysteresis as we try to roll this cylinder on this substrate. Because of the adhesion hysteresis, there is pulling in this region. So, the contact it does not open so easy just like that, and there is this. So, this is the advancing side, this is the receding side, and like this. Now, there is some amount of torque that needs to be applied in order to rotate, in order to roll this cylinder on this surface, and this is the distribution, the normal stress as a function of r. Remember, the cylinder center is at center line, is at here, the pressure is applied on this along this line. However, because of the asymmetry, in order to take care of the asymmetry, we use this kind of transformation where alpha is equal to b plus d. So, in essence 2b is the total width of this contact. So, that is why it is alpha plus beta is equal to 2b. So, here, and then the center of this contact area is actually here. From here we measure this distance r. Actually, I do not need to put r up to here, r can be put up to this point, and r. So, r is equal to x is equal to r plus d, because d is the center, this point, this position from the center of this cylinder. So, this is d over here. So, x is equal to this r plus d, that is all has been done, and we get this. So, we can determine d, we have to determine d, we will show you how to determine that. So, here we can do it for experiment. Now, we also determined that what will be the normal stress at the receding angle. Receding angle means here at that is plus b, here at r tending to plus b, we derived this expression, and this can be written as something like this. So, this quantity we derived it by writing this sigma r in this particular form, b plus r, here write is square root of b plus r into b minus r, square root of b plus r into b minus r, and we have shown that in the last lecture, and then we have this expression. So, here you see k 1, and I have described it earlier, this is called the stress intensity factor of mode 1 crack, will be given by, here it is given as 1 by square root of pi into b, and here minus p over pi plus that is E star by 2 r into b square by 2 plus d into b, like that. And so, the fracture energy or the energy release, strain energy release rate, it is equal to k I square by 2 E star, and so that term comes out to be here 1 by 2 E star, and this is pi by b, and then it is minus p over pi plus this is E star over 2 r into b square by 2 plus d into b whole square. So, this is the expression for the strain energy release rate, and I have described that in for brittle fracture. So, what we have here, we have the fracture at the interface without any irreversible process. So, therefore, this G I, that is the strain energy, whatever is stored in the material at the contact line or at the crack tip, that gets released, and that leads to the creation of the new surface, and therefore, that energy can be equated to work of adhesion or W or WA, whatever is related. So, this WA, it is the receding side. So, let us write it WR for me. this is in the receding side, receding edge. So, we are like this. And now, advancing edge also we can write. So, here I will write it as again E star, this is 2 into r, and here this is b minus r into b plus r, and here okay, it is whatever it is p by pi into square root of b minus r into b plus r, like this. So, here also I write here r tending to minus b, because this is the advancing edge, minus b here, and here also r tending to minus b here. So, here r is tending to minus b. So, I put it minus b here. So, it will be E star by 2 r, and it will be minus b. So, it is 2 b, and here it is r plus b. Here it will be r is equal to minus b. So, it is b square and minus b square by 2 and minus d into b. So, here therefore, let me write it completely. It will be b square by 2 minus d into b here, and then here it is minus, this is p over pi, and this is square root, and instead of in place of r I will write here minus b. So, it is 2 b here, and here it is r plus b. So, the singularity is taken care of, and therefore, in the same way that I did earlier, I can write it here as, let us say I write it here 1 by square root of 2 pi into r plus b, right, and then I can write into, this is 2 pi. So, square root of 2 pi. So, I have here 2 pi, yeah. So, b into square root of b into pi, right. This is minus over here. So, it is 1 by square root of 2 pi, square root of 2 pi. So, it is 1 pi is involved. So, b, that is fine, and then plus this is E star over 2 r, and again here square root of b here. So, I have 1 square root of b here, and square root of pi here. So, I have to have a pi here, square root of pi should be here, I guess, right. Yeah, and then here I have b square by 2 minus d into b. So, here this term can be written in somewhat differently, 1 by square root of 2 pi into r plus b, and let us say this is, I write it here square root of pi. So, it is square root of pi by b, let me write square root of pi by b. Did I write it earlier like this? Square root of pi by b, right. So, here let me write it as square root of pi by b, then it will be minus, this is p by pi, and then plus square root of pi by b. So, it is E star by 2 r, this is b square by 2 minus d b, and like this, yeah, like that. So, this term again, this is the stress intensity factor, but this is at the advancing edge. So, this is k I is like that. So, therefore, I write it as k I by square root of 2 pi, and here it is r plus b. Remember that this b is coming out to be plus b, it comes out because it is like this, and this point is actually minus b here, minus b, and then r plus minus b. So, this r plus b means this is the distance from this point, okay. So, along this distance. So, r plus b will be any distance from this point within this region, that is what the r plus b will mean here. So, this is all it is. So, k I already have. So, therefore, we can write now is the G is the strain energy release rate, this is in the advancing edge. So, this is advancing edge, and here this fracture energy is the work of adhesion, this is comes out to be k I square by 2 E star. So, 1 by 2 E star, sorry about that, 2 E star. So, it is E star and k I square. So, k I square will be pi by b, and here it is minus p by pi plus this is E star by 2 r and b square by 2 minus d b and square. So, this is the expression for, and this is advancing, let me write it A here, right. So, I wrote it here W r, this is W r I wrote, and here I have derived the expression for W A. So, that is the work of adhesion, okay, at the advancing edge. So, if you see these two equations that we derived, I have derived all this, we will see that the equation will show that actually it will show that here it is minus dB at the advancing edge and the receding edge it is plus dB. So, that will show that this W r is actually greater than W A. So, here let us say I have derived here. So, it is minus dB here and here it is plus dB, where it is here it is plus dB receding edge. So, therefore, this quantity W r is actually higher than W A. So, that is the hysteresis that we have here. So, that is the hysteresis, and that hysteresis actually depends upon this quantity d. If the d is large, then the hysteresis will also be large, and if the d is 0, that hysteresis is actually 0. Now, how do I determine this quantity hysteresis? So, that help me determine. In order to do that, we experimentally we measure this torque. Okay. So, we apply the load and let us say we apply the torque, and we can relate this torque to d, that is the idea. So, basically here this is the experiment in which let us say this is not full cylinder, but half cylinder, and then we have this plate let us say attached to this top half surface, this flat surface of this cylinder, and then we apply the torque over here, we measure it torque, and the torque can be related to the quantity d. How? Now, torque will be equal to given as this quantity, okay, r plus d into p r minus b to b, and so you substitute the expression for p. Okay. So, in terms of normal stress it can be written as in terms of sigma r, actually I should write sigma that is fine, but it is a stress, this is not Poisson, you should be careful about that, and it is a function of r here. So, now you substitute that expression over here. So, it will be therefore minus tau, and that is basically the magnitude of the torque. Okay. Then here minus b to b, and this is r plus d. So, let me write it E star into 2 r and b square minus r square half, okay, and this is r square minus b square by 2 plus d r, and this is r plus d. So, let me multiply it here r plus d, and here again let us say minus b to b, and this is p into r plus d, and this is pi, and this is b square minus r square by half. Here also I should have dr, here also I should have dr. So, now this quantity will be equal to E star by 2 r, okay, and then I have here minus b to b, and then I have here square root of b square minus r square, and then we have to multiply it by r plus d into this quantity into dr minus, let us say it is p over pi, and then I have minus b to b, okay, write properly, b to b, and here it is r plus d into square root of b square minus r square into dr. Now, you see the integration is not all that difficult, because you have to remember that this is a symmetric integration, symmetric minus b to b. So, therefore, that those quantities in the numerator which has got the odd number of the exponent of r, so those will cancel out, okay, and those quantities which has either r to the power 0 or r to the power some even number, they will stay. Okay. So, without doing much we can just get rid of those terms which, for which case we get r to the power some odd number. So, therefore, it gets simplified. Okay? It is we do not need to do all that calculation. So, here for example, what I will have here therefore r plus d. So, r cube term over here will go, here b square by 2 into r, that will also go, and then r square term will be there. So, it will have d into r square, that is one term, and then plus d into r square, another term over here. So, another term will be there, d into r square, and then d into minus b square by 2, that term also will be there, d into minus b square by 2, that term will be there. So, see here r into r cube, so that is an odd number. So, therefore, if you integrate from minus b to b, and this quantity b square by r square, okay, that is even, I mean that is that is even. So, therefore, this r cube terms will get cancelled, then b square by r term that will get cancelled, r into d r the d r square that will remain, and again d into r square that remains, and d into minus b square by 2 that will remain, because d into d, that is d square r, that will get cancelled, and over here in the denominator I will have b square minus r square. Hope it is clear to you. This is dr, and then minus again here minus b to b, this is p over pi, and here again the r by this r term over here. So, that will get cancelled, only thing I have to worry about therefore is p into d is there, and therefore, it will be p by pi 1 by square root of b square minus r square dr. So, I have simplified my integration by this manner. So, rest is just easy. So, here that is all I have, and I can simply integrate it very easily, rest of the things. So, I hope that I have simplified it, I guess. No, I did not simplify it, I should have it. So, finally, it will come out to be like this because of all those calculations that I did. So, here it comes out to be like that, and you can easily derive it. I am not going into the detail over there. So, d by 2 r, and this is minus 2, and there is a relation available for this square root of a square minus a square, and I think it is a into square root of a square minus a square. So, I think that term goes. So, only thing that will be there is sine inverse term. So, here so this term comes, so this will get cancelled, let me just write it. So, it will be just minus 2 into one term will be there with respect to r, and here since it is minus r by 2 to plus r by 2. So, this term will get cancelled, and then I have here plus, this is sine inverse, I will have x, so it is r by b, and it will be minus pi by 2 to pi by 2. So, from this I will get this, I hope this is correct, b square by 2 is there, b square by 2 is there. So, b square by 2 will be there, right, and plus it is 3 b square by 2 plus it is 3 b square by 2, and this is sine inverse. So, sine inverse it is 1, that is pi by 2, and minus 1 minus 1. So, it is sine inverse 1, so pi by 2 is pi. So, it should be pi here, and this is done here, and here also this pi also comes in the same way. So, please see all the slides. So, this sorry about that, this is pi here. So, this pi gets cancelled. So, finally, you will get some results, so which I have written here. So, no big deal. So, this way we get. So, finally, we have therefore this d is equal to minus tau. So, remember this is equal to minus tau, that is basically the magnitude of the torque, and divided by this quantity minus p plus e star into b square into pi by 4 r. So, what it means is that suppose we have the load, we do not apply any load is released. So, p is actually equal to 0, and then we try to roll it. So, we have to apply some amount of torque. So, what is the torque? So, the torque goes as whatever. So, torque we can measure, and from that we can obtain what is this d over here. So, that experimentally can be determined. So, that can be done. So, it is by this process, and we can also do estimate the hysteresis. So, for example, that the W r and W a we have derived it. Let us do it like this. Let us write square root of W r. Square root of W r will be square root of pi into 2 e star into b. here and into minus p by pi, okay, plus this is E star by 2 r into b square by 2 plus d into b, and here let us say square root of W A. So, that is receding and this is advancing, and as I said that the work of adhesion in the receding is actually larger than the advancing. So, it is like that. Now, here again we get it pi by 2 E star into b, and here it will be minus p by pi plus this will be E star by 2 r into b square by 2, it is minus dB, like that. So, if I add these two quantities, what do I get? If I add it. Okay. So, now let us do one thing, let us add it. So, if I add these two, square root of W r plus square root of W A. So, that will be equal to, this is square root of pi by 2 E star into b, and this is minus 2 p by pi plus this is E star by 2 r. Okay, so, b square by 2 plus b square by 2, that is actually b square here, and plus dB minus dB, that gets cancelled. So, I get it here minus 2 p by pi plus E star by 2 r into b square. So, that is where I get it. Now, let us say that most cases this p will be quite small. So, p will be quite small. So, let us say that p goes to 0 here. So, then I think when initially the contact is just made before rolling, right. So, then we have advancing everywhere. So, therefore, there this p is equal to 0, and then this we have for that the square root of W A, okay, from here p is equal to 0. So, I directly get here this quantity. Now, when it has before it has started rolling, remember that the contact width there is actually 2 b 0, right, and now when it starts rolling, after it starts rolling, so I have got contact width is little larger, that is b here. So, in the experiment I can measure this b 0 and b, and if I have an idea of W A, I can actually calculate what will be my W R, that is what I would like to show. So, here W A square root is equal to this, because p is equal to 0 here. So, I write here p is equal to 0, I get this particular expression. And same way, let us say that p is very small or almost equal to 0. So, therefore, in this equation also, okay, I get rid of p here. So, let us say p is equal to 0 here. So, therefore, I have 2 and square root of 2 pi star b and pi star b square by 4 r from here. And so, therefore, I can now divide this W r square root plus W A square root divided by W A square root, and I will get here, this is yeah. So, what do I get? So, I will get here, this is, let me write it, 2, and this will be square root of 2 here. So, square root of 2, let us say it is square root of 2, this is pi, this is E star by b into this is pi, and this will be E star into b square by 4 r. Remember here it is actually square root of pi and 2 E star into b 0, this is b 0 here, okay, and this is E star and this is b 0 square by 4 r, like that. So, here this is b 0 and this is b, so do not get confused. So, b 0 is here and b is here. So, now we can cancel this pi star, this is star over here, and I think some pi also goes out. So, this 4 r also goes, this 4 r also goes. So, in a sense what I should have is square root of 2 here, this is square root of 2, there is a square root of, this is square, there is a square root of 2 so 2 is there, okay. So, 2 is there. So, what do I have? I will have square root of 2 here, and then I have the b square by b square. So, b to the power 3 by 2, b to the power 3 by 2 I will have, okay. Again here I will have b to the power 3 by 2, Okay, what happened to my pi? So, I think a pi I get here most probably I should get a pi, no pi, yeah, pi should get, yeah, the pi I should get, yeah, I think that is it. I hope this is all right. Maybe this 2 there is a little bit of problem, but I think that I have sorted out anyway. So, here whole thing comes, so there is 2 also comes over here, right. So, finally, you will get here this work of adhesion in the receding side, W r square root will be equal to W a square root here like that, and this is 2 into B by B 0, this is to the power 3 by 2, okay, and minus 1. So, this is the way this equation captures this hysteresis, and so in most cases let us say we know this W a is from the thermodynamic work of adhesion. So, W a let us say we know for these 2 materials, and in the experiment, okay, we see that B 0 is different from B. So, there, okay, from the ratio we can actually estimate, okay, what is this W r. So, I can give a small example here. Let us say W a is equal to 44 millijoule per meter square and B 0 is equal to 2 millimeter, B is equal to 4.5 millimeter, and so you substitute this 4.5 divided by 2 to the power 3 by 2, okay, into 2. So, eventually it comes out to be 1.455 joule per meter square. So, you can see this is about 33 times bigger, okay, than this quantity, and this small difference B 0 to B, this is not actually that small, that captures, okay, this effect. Yeah, so it can actually estimate this work of adhesion by that. So, that is all for today. So, thank you all for your kind attention, and I will take up this a new topic in the next lecture. Thank you.